Hello and welcome to today's webcast brought to you by LEDs Magazine. I'm Editor-in-Chief Maury Wright, and it's my pleasure to host today's presentation, Designed by Data, Solutions for IES LDT File Creation. Today our presentation will come from Austin Peel of Radiant Vision Systems. We'll get started in just a moment, but let me just make a few announcements first, cover some logistics. I'd remind you that the presentation is live and interactive. You can ask questions at any time just going to the Ask a Question area there below the presentation window. Type it in. No need to wait until we actually get to the Q&A session. I'd like to thank our sponsor, Radiant, today for making the presentation possible. And again, for those of you in the audience, for your convenience, we will make this presentation available on demand within 24 hours of the live event. You'll get a direct email link to that presentation, and you can always get to any of our archived webcasts. Just go to ledsmagazine.com and go to webcast up in the top navigation area. Also, we are going to make this presentation available for you to download in PDF format today. If you want to download that, go to the Event Resources tab below the question submission box in the lower portion of the console. You'll be able to do that. Also, please note that you can view our webcast, of course, on PCs and browsers, but also on mobile devices, and that's true of the archives as well. Now, it gives me a great pleasure to introduce our speaker. Austin Peel is an application engineer at Radiant. He's a real lighting expert, a lighting measurement expert, and he supports their global customer base in looking at helping that customer base learn how to use the best practices for light measurement using Radiant systems. Austin got a BS degree in physics from the University of Washington, Seattle, where he was deeply involved in optics laboratory and CCD-based research. So welcome, Austin. The floor is yours.
Thank you very much, Maury. Hello, good morning, everyone. I'm Austin Peel. I'm an applications engineer here at Radiant, as Maury said. We are Radiant Vision Systems, a world leader in light and color measurement, and we have been providing scientific-grade measurement solutions for nearly 25 years now. We're really excited to get to share with you today the details regarding our solution for light source characterization and IES LDT file creation. As an outline for today, first, we're going to talk about what solutions are currently available for light source characterization and IES file creation, such as conventional far-field goniophotography and the near-field measurement system. Next, we're going to talk about how these systems work, how a measurement is collected with both of them, and what types of data you can get with each as well. What do we mean when we say near-field or far-field data? We're going to talk about that, and then I will do a quick demonstration within NFMS software, working within it to show you how to set a measurement up, as well as what the data looks like post-measurement and how to export an IES file from the measured data. Then we'll talk a bit about LM79 certification, and finally, we'll finish up with that Q&A session. All right, so let's get started here. So photometric data files play a large role in lighting communities all over the world. We use these data files in their various formats to help us understand the properties of light sources which most affect how luminaires will perform in a given setting. For example, quantities such as the total light output, total flux of the luminaire to the spread of the source's distribution throughout a given space. These data files are used as a common medium for sharing and studying this type of information and have become vital to properly simulating lighting performance through optical design and CAD-based modeling. Two very common formats to these data files are the IES format in North America and the ILLUMDAT or LDT format in Europe. So an IES file is essentially a map of the luminous intensity distribution of a light source, specifically the intensity unit candela in relation to view angle. The graphic here on the left shows a view angle radar plot of a luminaire's luminous intensity distribution, as well as a polar diagram highlighting a cross-section of that intensity plot. If you're looking at a data point in the center of the plot, this corresponds to a normal view of the source, looking straight on. As you move outward in any direction across the plot, this is equivalent to the intensity behavior as you rotate the source away from you in the corresponding direction. Alternatively, you can think of your cursor placement on this plot as corresponding to your view angle of the source itself. Next, on the right, we have an IES file viewer looking at the same radar data. However, in this case, a data point at a greater distance away from the origin now corresponds to higher intensity values, rather than the false color representation in the graphic at the left. So this polar plot and this 3D viewer are kind of achieving the same goal of mapping our measured points to provide the full representation of the source with regards to luminous intensity. So the photometric data files themselves can be generated and created using near-field and far-field techniques in made-to-be dark lab spaces where the size of the lab generally will depend on the measurement solution itself. There are two solutions available for creating such photometric data files. Conventional far-field goniophotometry is one of them, and then next is the near-field measurement system. So the near-field measurement system utilizes an imaging colorimeter or photometer to capture images of the source, sampling millions of points with each capture. And a two-axis goniometer is used to achieve the various perspectives on that source. Since we are measuring the device in the near field, a small lab space will do. The far-field goniometer, however, will analyze one point at a time. Remember, the source is approximated as a point source in this case. And for that approximation, you need a large lab space, sometimes hundreds of feet, so that your spot meter or lux meter can contain the DUT within the acceptance spot of the spot photometer. So with conventional goniophotometry, there are two options. First, that the light source might be mounted on a two-axis goniometer, which rotates in both axes and would allow the entire intensity distribution to be sampled, or the source can be fixed with a flying mirror directing that light to the sensor. In both cases, the sensor is going to be a stationary spot photometer or colorimeter placed in the far field. So in this way, we would create a luminous intensity distribution by combining those point measurements together and kind of interpolating between them. In order to get near-field data, you would have to use a separate instrument altogether, and we're going to talk about that near-field data gathering in a moment. So this is an image of the flying mirror goniometer setup. The advantages of this more conventional method is that it is accurate. You do get the IES or far-field data, and it is LM79 certified. Disadvantages, however, it can be quite expensive and is going to require a very large lab space, again, sometimes hundreds of feet, depending on the size of your largest luminaires. Then there is an increased possibility for stray light because you are sending the light over such a large distance, and there's also a large mirror involved in this case. You must be very sure that your spot photometer down at the other end of the room is not seeing any other light sources along the way, so typically you're going to have to use some kind of baffling options in order to achieve that. And the other option, if you're not going to purchase one of these far-field goniometers yourselves, is to send your device to a third-party testing lab. The idea here being that you can reduce costs by sending your device out for testing is the general idea. However, you only pay for an individual measurement. They're kind of unit priced, and it can require days to weeks, and in some unfortunate cases months, to get your device back and get the data for that device. So with external testing, there's a lot of time involved. An alternative solution is the Near-Field Measurement System, or the NFMS, from Radiant Vision Systems. The advantages to this system are that it's quite cost-effective, it's accurate, and you get two types of data. So instead of just getting the far-field data, you're going to get near-field data as well, and you can still generate those IES files within a minimal lab space. So it could be as small as just a couple meters up to, maybe 20, 25 feet or so. There's no real size restriction on the upper end. The disadvantage is that it is not LN79 certified, and we're going to talk about that a little bit later in this webinar. So, how does the NFMS work? We're going to show you a little video here momentarily of our source mounted on the 2-axis goniometer, which will rotate, and then we place a stationary imaging colorimeter in the near field and align it to our lit device. The device is turned on throughout the scan while the imaging colorimeter is cued to capture an image at every goniometer stop. So we measure the luminance and color at all angles by taking images at each position throughout the distribution. And you can see in this video that we're about to play here that the overhead lights are on, but that's just for demonstration purposes. And in general, you'd want to have a dark lab space so that the only light that the camera is seeing is coming from your device under test. So let's go ahead and see that now.
Spectrometer measurements, actually.
Okay. So, using the imaging colorimeter, we allow the light source to not be treated as a point source. We are not recording the far field data alone, which assumes that all light is coming from the same origin. Instead, we record that spatial information from the near field and extrapolate that data out to infinity via the ray tracing method. At the end of the scan, you have hundreds of images that are combined to give you the complete characterization of the lamp or the luminaire. And the software can then produce the luminance and chromaticity as a function of angle and use that pixel by pixel data to provide a complete intensity distribution representation. So we've mentioned the terms far field and near field, but let's elaborate a little bit more on what those terms really mean. So a far field distribution means luminous intensity as a function of output direction. In other words, the luminous flux per unit solid angle in angular space. A far field measurement assumes that you are far enough away from the source that it can be approximated as a point source. So again, all light is coming from a point in space and goes outward in various directions. The near field measurement, however, does not assume that the light source is a point source. You are close enough to the source to make out the spatial variations across the lamp's surface. And in fact, what we do is measure light according to its spatial origin on the lamp and the angle at which it is emitting. We are capturing the spatial variation as well as the overall angular data when using an imaging colorimeter in the near field, which gives us a more complete data set than far field data alone. So your traditional far field system will require that high degree of straight light control. Again, because you are sending light over a very long distance, so there's a lot of room for error there. It doesn't use ray tracing to get the far field data, as it is a more direct measurement in that case, but it gives you minimal source information because really all you're getting is data about where the light is going from a distant perspective, and you don't know how that light behaves close up or even on the margin between near and far field. You also, again, need that large lab area, which is going to be proportional to your device size. So if you're working with large luminaires, for example, the space required can get quite extensive and expensive depending on your lab space resources available. The near-field system, on the other hand, requires very little space. You don't need a tunnel with many large baffles to block out that bit of stray light, as the software can simply ignore it once it's configured. So all you need is a standard dark room, dark walls, dark floor, and a dark ceiling. Doesn't have to be large, just large enough to accommodate your largest device under test while it's rotating about on the tabletop-sized goniometer. The resultant NFMS data can even be used in ray tracing software to accurately describe the exiting light and incorporate those into your model or to simulate the illuminance distribution at any distance from the source. So rather than just at an infinite distance away from the source, you can see the illuminance pattern at an arbitrary distance from the source. Perhaps you wanted to see it a meter away from the device. You could test that and then move it as well, simulate as well as 5 meters away. You could test that and see how the distribution changes between those two distances. You're also going to get the luminance data, so we can even provide a glare rating for your light source over angle as well. The NFMS measures near-field data. It gives you more information than your far-field-only measurement because it doesn't treat your light source as a point. It considers that spatial information of where your light is originating, and it can predict the illumination pattern at any distance from the source. By measuring the near-field data, we're able to get both that spatial data that you need for software modeling from close up to mid-range to far away, and that angular data you need for IES files. So the frame of the NFMS is designed to hold large or small luminaires, so it can facilitate devices down to the tens of centimeter range and up to about 2 meters depending on your device shape, weight, and size. Again, we can produce those near and far field models with just one scan, so you don't need multiple devices, just both data sets all at once with the same measurement at the same time. So the resulting data consists of luminance measurements, and in those measurements you can get the chromaticity according to its spatial location on the source. We can again calculate the illuminance distribution at any given distance. We can see the near field distribution of light as well as that far field distribution, which is gathered again by ray tracing that pixel by pixel information. And if you add on the spectrometer option, you can see a larger variety of color and spectral data over angle in addition to the pixel-by-pixel chromaticity coming from the colorimeter. Now that spectrometer is an illuminance spectrometer option that will capture measurements in tandem with either the colorimeter or photometer that you would acquire with the system, whichever suits your needs. Regarding view angle performance, a major benefit of that spectrometer addition to the colorimeter is that you can see how the performance of your light source changes as you're looking at it from different angles with respect to quantities such as correlated color temperature, CRI or color rendering index, and UGR or unified glare rating. The data output, so you can output and export this data into a variety of formats. You can make IES files, LDT or IllumDat files, as well as radiant source model output formats, which you may refer to as ray sets. And here's just a short list of the supported formats currently for exporting those ray sets within ProSource. So you can use ProSource software, which you get in addition to NFMS, in order to export ray sets that can be used in a variety of optical modeling software programs listed here. This is just an example of what we had talked about before with seeing the illuminance distribution at any arbitrary distance from the source. So let's say your goal is to, for example, simulate the illumination of a light that is placed under your countertop or in a cabinet or under a shelf or duct. You can do it with a near-field measurement. You wouldn't be able to do this accurately with an IES file alone because the IES file can only predict what's going to happen very far away from your light source. But in the case of cabinet lighting and the like, you're not working very far away from your light source, and the spatial extent of that source is going to matter in the illumination pattern that's created on the surface that is closer to the source. So how does the NFMS compare to conventional goniophotometry? Well, it is a complete data set, and all of that image data is retained for further analysis. You get hundreds of highly resolute photos of your source, which accurately capture the outputted luminance and color. You get the spatial and angular data of your source so that you can create those ray sets or IES files with that intensity information. It's cost-effective, especially when compared to a traditional swinging mirror goniometer, and you get fast results with virtually no turnaround time using this in-house measurement system. Within just a couple hours for a single light source, you can get that data set. Not to mention that you can use the camera for other measurements as well. It's not tied directly to the goniometer itself. It's not fixed to the system. So you can use that camera standalone to measure displays. You can measure illuminance patterns with that camera. And as far as accuracy, we have proven that the NFMS far-field result is within 1% of reference measurements, so within 1% of what conventional goniophotometer will provide. Moving on, let's discuss the kinds of engineers who can most benefit from a system like this one. The answer is anyone who needs to characterize the view angle performance of an emitting device. In this case, we talk a lot about luminaires, but it can really be any light emitting device with dimensionality greater than about 10 centimeters. The near and far field intensity distribution data that you're going to get from the NFMS is helpful if you're going to be doing software modeling, or if you need to give data to lighting designers who will then use it in software. We can do the luminance distribution for large and small light sources, and again, these files can be used for architectural lighting applications or for designing the lighting within large and small spaces of light. Very important, again, within the lighting community is the IES and LDT file formats. The IES format being a US standard and the LDT format being a European standard format. They both contain that far-field data set, which you are going to get from the NFMS. Now, what about LM79? Mentioned it at the very beginning of the webinar and said that the NFMS is not LM79 certified, and that's because the NFMS plainly was not designed nor intended to be a certification goniometric system. One requirement for such a certification is that the light source be measured while orientated the same as it would be when it's in use. And with NFMS, you simply mount the source in a horizontal emitting orientation. Now, for most light sources today, which are LED driven, there's little to no difference that exists between the output of a lamp aligned in one orientation versus another. But in any case, that is simply not the focus of the NFMS. It is designed to be a flexible and multifaceted data gathering tool that provides a more comprehensive look at lighting performance. So what you can do is create those IES files that are going to be just as accurate as those you receive from the third-party lab, and you'll be able to verify that your lamp is going to pass your LM79 certification before you even send it out, which saves time and money, especially when your product line involves continuous modification towards improvement, like many product lines do. The value, again, lies in that pre-certification testing, by making sure that what you send out is going to pass rather than having to send out multiple iterations and paying for testing on each one of those iterations and having to wait for your results for each one of those iterations. You're also going to be able to build that source model library of IES files and radiant source models, which your customers are surely going to need when using your products. So now we're going to move over to the software, and I'm going to show you how to set up a measurement and then do some analysis of the data and export of an IES file. So let's go ahead and take a look at that.
Okay, so now we're going to move over to the software demo. I'm going to start out by showing you how to set up a measurement briefly using the checklist over here on the right, and then we're going to do some analysis on the data and demonstrate how we export an IES file. Okay, so entering active alignment mode, we have aligned our camera in front of the NFMS, making sure that the height of the camera and the offset from a known reference, such as the wall, has been verified. We have also optically aligned the system so that the camera's center optical axis and the center of rotation is well defined. We have also taken care to focus the camera and auto-adjust the exposure time. So moving on, we're ready to go down the checklist and verify that all the software settings are correct. We have entered in the source information the camera distance. The camera distance here is listed as 1.4 meters. The source type is an LED module, and the model number is a 147A. Serial number is 5281, and this is a manufacturer unknown LED, so we will just put that in here, unknown. Scan environments down here will allow you to enter parameters in the lab environment, such as humidity and temperature, and it records these within the radiant source model, so you can look at them later. Now we'll move on to select our measurement setup. We've selected our measurement setup to be color 1x1 binning, for which we will be taking photopic measurements today. Now we can go ahead and verify the lens settings. We can trust that the Canon software controlled lenses are set correctly. We've already performed the alignment and field of view scaling. That's basically just an image scaling. We've mounted the power, making sure that we have mounted the source and routed the power throughout the system in such a way that none of the cables are going to hang up on any of the rotating bits there. We've also verified there's no motion restriction by moving the NFMS to its full range of motion in order to verify that nothing is going to snag. We've refined the source alignment, and if you follow any of these blue hyperlink checklist items with a right-click function, it actually brings you to the appropriate software window here. In this case, it's the active alignment window for the refined source alignment step. And again, we can see that we align properly there. Moving on, we've allowed the source to warm up. In this case, we've waited about 15 minutes. We can also record the source power settings. This just brings us to the system information menu where we can record how we're powering our source. Next, we're going to turn off the ambient lights so that the only source of light that we're measuring comes from our device under test. We've already set our exposure times once, but we might as well check those again. Here we're adjusting the green filter to 70 milliseconds to reach a saturation level of 75%. That's perfect for what we want to see. That's optimal. We'll go ahead and save that. Next, we'll verify our subframe region. This allows us to apply a static crop to all measurements so that the data size of the entire radiant source model file is minimized. Basically, this allows us to just ignore all the pixels outside of our subframe region crop and to have that data not be included because it's basically looking at nothing but dark. And step 15 is a bit similar, although instead of a static crop that is physically defined, this is a image by image illuminance crop, which is defined based on a threshold of the max gray that the camera measures. So this is kind of a active crop on the sensor to make sure that the sensor is just imaging the area of the light and the actual active pixels of the light source for its data acquisition. So it's basically a second layer on that data size control, and allows us to apply an image crop and a threshold that's based on, again, the percentage of maximum gray value that we measure for each image. 0.2 and 0.2 is a very common setting. We don't need to threshold too much in order for all those dark pixels to be ignored. So 0.2% and 0.2% is great. That allows us to really crop down and only record that source. So next we're going to move on to step 16, and that is perform a brightness scaling or a color calibration if you want. Today we're going to just use the factory supplied calibration. Then finally step 17 is to perform the scan. So now we can go ahead and specify our inclination range from 0 to 90 degrees. We're going to go ahead and do 10-degree increments. And then we'll go ahead and specify our azimuth range to be 0 to 360 in 15-degree increments. And that's going to give us a total of 179 measurements pending. We're going to go ahead and add those to the queue, and then we auto-populate our list there, and we can go ahead and start the scan. So now, about 30 minutes later, the scan is finished, and we have our results. So if I want to go ahead and look at these results, I just open them up in NFMS or ProSource software. Here we're looking in NFMS, and we're going to go ahead and check the near field intensity, which looks very symmetrical like we expect. We do have some eccentricity here caused by the fact that the source we're looking at is rectangular and not square. But what we really want to look at, and what I really want to show you, is the IES file. And so for that, we are actually going to close NFMS and open up ProSource software. ProSource software is the software where we turn our radiant source model files into things like IES files and ray sets. So here we have our file open in ProSource, and to generate the IES file, we just need to have an intensity radar plot traced out to infinity. So we go ahead and go to generate the far field intensity option, and we specify the number of rays which we'd like to trace out to infinity. We're going to go ahead and use 10 million rays for this generation. I'm going to go ahead and wait for that to finish. And this is where the software is looking at all those camera pixels, finding the points of origin for that light, and tracing that ray out to infinity based on its, taking care of things like its origin and its direction and its intensity. So here we, now that we've successfully generated the far field intensity plot, we can use this to generate the IES file. We can use the preset defaults in the IES file generation window, such as inclination angle increment and azimuthal angle increment. We can have them increment at 1 degree at a time, or we can go lower resolution or higher resolution. Basically depends on kind of what you think makes the plots look best and how your customers would want to see that data. You can kind of have some flexibility there. So yeah, that's what we want to replace. We want to go ahead and replace the IES file that I already generated earlier. I'll go ahead and name it what we want and replace the file. And now that we've created that file, we can go ahead and open it up in an IES file viewer. And as soon as this loads here, okay, yep, there it is. And we can see a nice symmetrical distribution like what we would expect in our IES file viewer, as long as all the source information that we put into step 2 of that checklist.
Okay, great. So in summary, photometric data files, i.e. IES and LDT, offer critical light source measurement data for lighting design, such as the luminous intensity distribution, the overall output or total flux, and the angular spread of that light. Two solutions for IES LDT file generation are conventional goniophotometry and the near-field measurement system. The near-field measurement system has some significant advantages over conventional goniophotometers for near and far-field data acquisition in terms of cost, speed, size, and lab space, and offer equivalent accuracy. Radiant's Prometric NFMS, Prometric Near-Field Measurement System solution, consists of an imaging colorimeter, a 2-axis goniometer, the software itself for generating IES LDT files, as well as the Radiant source model itself. PM NFMS software creates these photometric data files in IES or LDT file formats, which can be output as polar and cone diagrams using any common optical design program. So now that will conclude our webinar, and we're going to go ahead and have our question and answer session, which will be hosted by me. You should be able to enter questions into the text box on your screen, and we'll be able to see those questions. We'll read them out and then provide answers during the Q&A session. If you are unable to attend our Q&A or you don't have time to stick around, thank you very much for your attendance. And if you have any questions, please don't hesitate to contact us. And the best way to reach us would be to simply email info@radiantvs.com. One more time, info@radiantvs.com. Thank you all very much.
We have some good questions that we'll get to now. And for those of you in the audience, apologize again, but there's still time for you to ask questions if you would like to. Austin, this person referred to your under-cabinet example that you used and said, could you describe what the negative issues would be if you measured this as a point source?
Okay, yeah, okay. So I take that to mean basically what are the negative issues you might run into if you use far-field data in a near-field simulation. And the answer kind of lies in what type of source it is. For example, for a single source that is already a very close approximation to a point source, and what I mean by that is kind of like a small singular LED or singular small LED array, the difference would not be as great if it was, let's say, an LED strip or an LED or a kind of a length, a dimension-oriented luminaire. So basically, if you have a string of LEDs and you're modeling what that illuminance distribution looks like a foot away, well, you can imagine that with a string of LEDs, you're going to kind of see that interference is going to be kind of present in the way that that light gets distributed across the surface, meaning you'll kind of see non-uniformity in the illuminance across that array. Now, if you only have far-field data in order to simulate that, what you probably won't see, you probably will not be able to see that that kind of non-uniformity in the illuminance distribution itself. So that's one of the advantages is to having that near-field data and to being able to do that ray tracing to a close surface, is that you can actually see where your illuminance peaks and valleys, as it were, across the surface.
Kind of the opposite end of the spectrum, I guess, from that question would be, how large of a light source can the near-field measurement system hold or handle?
Yeah, that's a good question. So our standard kind of, this is what we'll say the first time somebody asks, is about 2 meters in length. But really it's going to depend a little bit more on kind of the size and dimensionality of your source and the weight. So there's a weight specification to the NFMS 800 model, and that is that your source shouldn't weigh more than 25 kilograms. And then there's also a weight specification to the NFMS 400, and that is that's like the little brother to the NFMS. It's a slightly smaller goniometer, and that weight specification is 5 kilograms. Now, as far as size is concerned, it's not a huge issue as long as your source is within that weight specification, and as long as it's able to be mounted to that aluminum stock frame relatively well. So again, you want in the NFMS case your device to be underneath the weight specification and to be able to mount to that frame as well as possible. And then, of course, if you have further questions on that, you can always interface with us here at support@radiantvs.com in order to understand a little bit further how this might work for you.
Here we have a question really looking for maybe a comparison with what you've described and what maybe might be considered a more legacy approach. Have you tried two methods, near field and far field, by your method using ray trace against actual near and far field for the same sample, and compared the two sets of results and how far off they were in terms of those actual results?
Oh yeah, that's a great question. So we often get this question from our new customers and our prospective customers, and typically the way we'll handle it is we'll just say, okay, send us your luminaire. We're going to do a proof of concept measurement for you and measure it on the NFMS, and we're going to compare it to your conventional goniophotography results or your far field results, and basically what will typically happen is we'll get a sample or we'll get an example of one of those far field results and use that as our means of comparison. And what we've seen is that from a total flux and an intensity over angle standpoint, our results are within just a single percentage point off from the actual far field result. Now, I'm not exactly sure what is meant by actual near-field measurement for that sample, because as far as I can tell, an actual near-field measurement would just be, well, let's take an illuminance meter and put it really close up to the source and just kind of approximate the source as a point source close up, and do that intensity mapping, and actually, the results are going to be the exact same in that kind of case. We're going to be spot on with one of those illuminance meters close up as well. So yes, we have done this experiment multiple times, and we kind of do come back to it again and again for proof of concepts for prospective customers. So good question.
So it's a question about the equipment. What kind of camera is needed for the near-field measurement system? Are there limits on what I can use?
Yeah, the software is written to interface with our Prometric imaging colorimeters or our imaging photometers. So you can use any of our released imaging colorimetry or photometer products. The I-Series is going to be a colorimeter and is going to be able to measure color for each of those point measurements, pixel by pixel. And the Y-Series is typically going to be a photometer only. That's kind of a smaller version of our cameras without the moving filter wheel component, and it basically will either have just a photopic filter in the optical path, or in some cases it'll even have a radiometric filter in the optical path. So, and it is also possible to measure in radiometric units within the software as well. So basically any of our imaging colorimeter or imaging photometer products will be able to work with the latest renditions of the software.
So here's a question really about compatibility of the data sets. This person says, what about other lighting design software? Where can I use the data files obtained? And I assume the person means with your near-field measurement system, because they go on to say Dialux or Relux aren't able to use those files in their original format, so they must be converted into IES LDT files.
Yeah, right. So basically that's kind of the beauty of the flexibility of a radiant source model within ProSource software is we can basically take that radiant source model and we can export it into a format that was specified to us by those optical design softwares that I listed in the presentation, but that's not all we can do with them. We can essentially, again, format them into an IES file. So if your modeling software only accepts an IES file, then that's okay. We can still create that from the radiant source model information. And in the ray set generation aspect of the software, it's not just the specified formats in the list that we can export to. We can also export kind of generic ASCII formatted files or generic binary formatted files. And typically what will happen in those cases is, you'll use ProSource, you'll generate one of those ray sets, you'll try and import it into one of those, one of those other software programs, and if that doesn't work, usually we work with the support team for that software program and kind of understand what their expected format is and how easy it is to get to that expected format from one of the already existing export formats that ProSource currently offers. But most of them do accept a simple IES file format, an IES formatted file. So that's no problem typically.
But would you get more data if you support natively or if you have a way to use one of the ASCII type files? Would you actually transfer more data in that case than you would with the IES file?
Right. If you build a ray set, you're actually getting kind of spatial. A ray set is going to have kind of the rays listed in terms of their origin, their direction, and their intensity, while an IES file is basically, again, that kind of point source approximation. There is just an intensity value at a specific angle. So yes, you are kind of getting more spatial information with one of those exported ray sets, and we are always accepting suggestions as far as additional file formats to export to, and we do take that into consideration.
So this person asks, how many angles are measured by the near-field measurement system? Yeah,
if you are trying to build a comprehensive ray set, you can increase the resolution of the scan in order to provide more data points, more raw data points, and kind of less interpolation that way. I will say that for a typical scan, we're performing about 1,500 measurements over the forward distribution of a luminaire. And that with our latest NFMS software, thanks to some new speed improvements, only takes a couple hours or less. So that's really great.
In a very much related question, this viewer said, how can I reduce the length of time? It's taking many hours to complete one test at a time. Obviously,
right.
Time yields accuracy, I guess.
Okay, so for that person, I would say you definitely need the latest version of NFMS software. We've done some recent work with NFMS software to try and improve that measurement-to-measurement takt time, and it was the case that the overall takt time of NFMS software used to take more than just a couple hours for a high-resolution scan of a source, but that isn't the case any longer. So with the latest version of the software, there's significant speed improvements that really cut the takt time down to less than half of what it used to be. So if you're in software support, great. We can send that to you. Just email support, and we can go from there.
There's actually a question from a viewer about automotive lighting. Would this system be appropriate for the measurement of automotive lighting? And I assume they would mean maybe a module that might have been designed for forward lighting or something of that nature.
Absolutely, yeah. We deal with those applications all the time. So we have many customers who simply will measure automotive lighting components like tail light components or headlight components on the NFMS in order to again measure those intensity values at specific angles. So yes, that's absolutely an appropriate application. That's also a great case for the situation where you might use the camera as a standalone rather than the camera and the NFMS with that automotive lighting. For example, if you want to measure the illuminance distribution of your headlight, well, with the camera and the NFMS system, you can essentially measure the intensity distribution of your headlight on the NFMS, and then if you want to measure the illuminance distribution of your headlight onto a screen or projection wall, you simply move the camera over, face it at the projection wall, and you can move your light from the NFMS to a fixture aligned at that projection wall, and you can now switch to illuminance mode rather than kind of intensity mode as NFMS software uses.
This question that came in very early on, and it's probably something that was addressed during the course of your presentation, or even in that last answer you gave. But maybe you could summarize all the different metrics that you can measure with the system, all the different units.
Yeah, right. Absolutely. So where it all starts is the luminance measurement of the source. So essentially, the camera measurements themselves are measuring luminance and color spatially over the source, and color in the case of that you're using a colorimeter. And then each measurement is looked at kind of on a global perspective to give you an intensity value. And then after all of the intensity images compile up, a total flux calculation then takes place in order to give you the total output metric. So you're getting kind of the full suite of photometric units. You're going to get luminance on a measurement by measurement basis. You're going to get intensity on a measurement by measurement basis, and then you're going to get a total flux value on a model by model basis.
And this viewer had a two-part question, asked, does an IES file indicate what type of test measurement was utilized? And second, is there a translator for converting IES files to LDT format, and probably for vice versa?
That's a good question. Yeah, so typically there is an IES file format will typically have a space where the test lab name is going to be input into the IES file. I, however, would need to double check and to understand whether or not an IES file is specifically formatted for whether or not the IES file was created using a near-field measurement system or a far-field measurement system. I don't believe that's the case currently. But who knows, in the future it could be. And then, I'm sorry, what was the second part of that question?
And is there a way to translate between IES and LDT files?
Okay. Again, I'd have to look into that. I wouldn't be surprised if there was a way to translate. However, LDT files usually will have some more source-specific information with them, such as kind of the length and the width and the height of the luminaire. So there's kind of just a different set of static information that exists within the IES file that doesn't within the LDT file that doesn't necessarily have to exist within the IES file format. So my guess is that there probably is a translator out there somewhere, but that translator wouldn't be a simple single button transition from an IES to an LDT, probably because there's information that is present in one format that doesn't necessarily need to be present in the other. So that is a good question, and we could look into that.
And what about, this person asked, can your system be used to measure ultraviolet or infrared sources?
Yeah, that's a great question. So the sensors within the cameras themselves have a sensitivity range of about 350 nanometers to about 1050 nanometers or 1050 nanometers. So outside of that, not really. And inside of that, at the ends of that spectrum, the sensitivity kind of does fall off and become less and less sensitive towards those edges. But yes, it can be used to measure those wavelengths respectively. And typically, what users will do if they're interested in characterizing that distribution over those wavelengths is they'll purchase the system with a radiometric window installed. And what the radiometric window is, it's simply a clear window that doesn't attenuate to the tristimulus curves, such as the other filters do in the colorimetric system. So there is a way to do some of those applications. Those are typically understood within some discussions with our engineering team on a more case-by-case basis. But yes, it is possible. The sensor is sensitive, as I said, from 350 to 1050 nanometers.
Okay, well, we're getting to the top of the hour, so I think we'll wrap it up. On behalf of LEDs Magazine and Pinwheel Corporation, I'd certainly like to thank Austin Pill for a very excellent presentation and also some really interesting answers to the questions. Also, I'd like to thank our sponsor, Radiant Vision Systems, for making the presentation possible today. This webcast, Designed by Data, Solutions for IES LDT File Creation, will be archived within 24 hours. We'll be sending each of you who registered a direct email link to that archive. Go back and watch it as many times as you would like, and you can always get to all of our archive webcasts just by going to ledsmagazine.com and clicking on the webcast in the top navigation. So most of all, I'd like to thank all of you in the audience that took the time to join us today. I know your time's valuable. We certainly appreciate you spending some of it with us. So we thank you for joining us today, and we certainly look forward to serving you with future webcasts. Have a great day.